if you are studying statistics in university, then inevitably you are going to learn how to learn so-called hypothesis testing as an integral part of the inferential statistics. But do you really understand, or does the textbook actually tell you what you are doing? In particular, when you say, I'm confident to reject or not reject my non-hypothesis, where does this confidence come from? Now, today I'm going to discuss these issues. I'm going to use a graphical tool to illustrate my ideas. Let's go. So you can see I have created decimal files in which the blue curve, the blue bell shape represent a standard normal distribution, or which is used to do the z-test or z-statistic test. The purple color, the vertical purple color around 1.96 represent the critical value. Beyond that, the probability. So that area, normally called alpha or sometimes called half alpha, represent the 5% chance. So the thick blue vertical line represent my z-score or z-statistic, and which can be worked out by this empirical estimator. And that is a difference. Let me see. So this is definition of this is X, I use X, but actually Z. Is A represent the sample mean and U represent population mean of this particular data statistic study. And also you notice that when we use this statistic, the population standard deviation has been estimated by use S, which is a sample standard deviation, divided by square root n. N is a sample size. So if I just let you know what we have done here. So on the right-hand side, you see a bell shape, which is actually normal distribution, Gaussian line shape, which represent the distribution of the mean of sample mean. So mean of the sample mean is random. So each time you pick up different number of samples, you might get different sample mean. So that is why the mean of the sample mean is random. So we use this, but assume you have to, if you, according to central limit theorem, which states that the distribution of the mean of sample mean will gradually approach to the normal distribution. Okay, with if the size of number, if the sampling increase to infinity, so that is well-known central limit theorem. Now in this graph, I have drawn this the white color bell shape, which actually represent the mean, the distribution of the mean of the sample mean. Now, for example, if I change the estimator, for example, if I change the sample standard deviation, you will see that it also will change the line width or the population standard deviation as well. See, if the sample standard deviation is smaller, and then the bell shape or population distribution getting narrower. Okay. And it is noticed that the profile of this normal distribution is depends on several variables. S, which is sample standard deviation, is one of them. Another is the sample size. So if you use different, if sampling different number of sample, at a different time. So that is also dependent or determinant of the profile of the normal distribution. Right? There are two variables. Of course, this relation, the relation itself is just a hypothesis. It's estimate. We call it estimate. But the important thing I want to tell you now today is that if you look at this drawing, the origin curve, the vertical origin line represents the population mean. I set the population mean equal to 6. So the population mean is 6, okay? And the line, which is green vertical line, represent the sample mean. So each time you will get a different sample mean. Can you see? That is how sample mean can be different from population mean. Here I just consider that simplified version, that assuming the sample mean is always larger than the population mean. Okay. So you can see that if the sample means increase, you will see that the green vertical line shift. It is apparent no matter how small the sample mean differs from the population mean. From the graph on the right-hand side, we can always make the conclusion that the sample mean is larger than population mean. So therefore, there's no chance to not reject your null hypothesis, which states that the sample means equal to population mean. Still, in many cases, as you have been doing the problem solving, you will find that you can build a certain degree or certain level of confidence not to reject your null hypothesis, which is assume that the sample mean equal to the population mean, even if the fact, can you see that the difference is there? Of course, in real life, we really don't know sometimes. We don't know population mean. But another thing we don't know is another random variable called standard deviation. In this case, if you put, if you just change standard deviation S here, you will see that that will influence affect our z-score. So if we increase the sample standard deviation, the z-score will decrease. So in this scenario, so as long as the sample standard deviation is large, we can always confidently say that we will not reject the null hypothesis. In other words, in this, if the sample standard deviation is large, we can always tell people that, well, the sample mean equal to population mean, okay, because nobody can tell that difference, because the reason is that we don't know exactly what is the sample mean or the population standard deviation. To illustrate this point, let's just turn on the sample distribution, the distribution of the mean of sample mean. Okay, let's just turn on this population. This is population mean. This is a sample mean. Let's just turn on this one. Can you see that? The blue line, in this case, represent that the sample means with the sample standard deviation, in this case, is so large, equal to 2.3. If I reduce the sample standard deviation, you will notice that not only does the sample distribution change, you see, but also this z-score increase. At this moment, the z-score is exactly approximately equal to the critical point. So over this critical point, we can reject the non-hypothesis. Do you agree? So if we just continue, if we just continue to decrease that sample standard deviation, now we can confidently reject the non-hypothesis, which means that indeed that over this critical point, we will see that we will conclude the sample mean is different from population mean. So the reason is that we have reduced, if the sample standard deviation is small, and we can always, in many cases, we can confidently conclude that the hypothesis is not right, and hence should be rejected. However, another factor which influences your conclusion is sample size. At the moment, or number of tests. A number of tests is just 27. So if we reduce that one, can you see? If we reduce the n, the sample size, the z-score also decrease. Can you see? For the same sample standard deviation, if the n sample size is small, then you can still not reject your non-hypothesis. Can you see? The result change just because the number n is small. Of course, some people may argue that if the n is smaller than certain numbers, say 10, we should not use the z-score test. We have used a student statistic or t-test. That's okay. But to discuss this issue, we can assume that we can still use the standard normal distribution to do our z-score test. Right. However, if we increase this number n, you can see that they can easily go beyond that critical point. In this case, we must reject the non-hypothesis. In other words, in this case, if number n is big, then we can easily reject the non-hypothesis and to acknowledge that the apparent, in this case, that the sample mean is larger than the population mean. However, if we continue increase this one, if you go to another extreme, if they go to 100 sample size, oh, this is 155 already, and then we increase the standard, then we increase the sample standard deviation or uncertainty, you will know that this score reduce dramatically. So this is where, can you see, at this critical point, the standard deviation of sample standard deviation is 1.3. So below that critical point, in this case, so if the sample standard deviation is 1.4, then we can conclude that we should, not reject the hypothesis. So we change our mind. We change our mind easily. We change our mind just because the sample standard deviation change, or the size, the test, the n change, the sample size change. Okay. So you can see from this illustration, the conclusion in your hypothesis test depends greatly on uncertainties. Okay, so it could be argued that the confidence we talked about, the so-called statistical confidence or statistical significance is not built on the known fact. Instead, it is built on unknown facts, such as standard deviation and the mean of the sample mean. I hope this explanation will give you some new insight into the so-called hypothesis testing, which in my opinion is not reliable at all. Thank you.